Greetings from İzmir Institute of Technology. We are Cengaver Rover. Our journey started in 2022 with just 4 people. Today in 2026, we have grown into a dedicated team of 45 members. After competing in ERC23 and ERC24, with our newest generation of rover named Talos, we are now fully focused on our next big goal, ERC26. To stay organized, we operate through 5 specialized sub-teams: mechanical, software, electronics, science, and management. Each team has own sub-teams to define roles to ensure every detail of the rover is perfected. While we do our main development in our workshop, we take our testing to the field. We use the rocky and rough terrain on our campus to put our subsystem to test. It's a perfect environment to prepare challenges ahead.
Our rover features a 5 degree of freedom robotic arm inspired by Headington Dynamics Dexter architecture. Built from 6000 series aluminum at just 8.5 kg while supporting a 6.2 kg payload across a 95 cm reach. Powered by NEMA 17 stepper motors with 100 to 1 G reducers. The system uses a double-loop load feedback controls with absolute and precision encoders for accurate positioning. We define the desired end effector orientation and apply inverse kinematics to control the arm in test space, enabling precise autonomous operation across all competition objectives.
Our manipulator is controlled by a custom-designed 4-layer PCB based on STM32. It communicates with Jetson Orin Nano for command and sensor readings. The board drives 6 stepper motors using TMC2209 modules and magnetic rotary encoders.
Our rover is designed for extreme terrain. It features a compact 710 by 310 mm main chassis. This modular frame is integrated with a central shaft breaker suspension system, guaranteeing continuous 4-wheel ground contact over several obstacles. To absorb high-frequency shocks, our TPU95A printed tires utilizes an re-entered honeycomb. It's a re-entered auxiliary honeycomb geometry. This complete structure acts as a secondary suspension. Power is delivered through fully sealed top motors housed within each wheel, paired with a 1 to 100 planetary gearbox, 40 Nm of torque per wheel. This highly capable drivetrain ensures flawless mobility during steep slope climbs, sharp left and right turns, and precise forward and backward maneuvers.
The simulation team handles sensor placement optimization, autonomous driving and object detection. By simulating different obstacle types before the physical race, we can improve our algorithms without risking damage to the rover.
For instance, we recently tested object mazes and slope scenarios to improve our obstacle avoidance logic. We can also manually control the simulation by using the tools of the control subteam.
The rover's power distribution system uses a dual relay switching architecture with 7 24 volts 10 amps fuse protected relays and reverse voltage protection. An STM32 and 28 BGTs handle the safety logic, individually controlling power flow to the robotic arm, bodyboard, science kit, and 4 DC motor drivers. The red mushroom e-stop button drives 2 relay coils in series via AND OR gate logic. When pressed, all outputs cut instantly and only restore upon deliberate STM32 reauthorization.
The functions of the rover body is controlled by a custom-designed 4-layer PCB. The board drives 2 stepper motors for rotating with 360-degree camera, drives the headlight, controls the indicator lights, runs the cooling fans, measures pressure, temperature, orientation, and battery voltage. We utilize an STM32 G4 series microcontroller capable of motor control. Inside board, components communicate with the MCU using I2C and UART. The 3-color indicator light turns red when the rover is stopped, turns yellow when in autonomous mode, and turns green when manual operation mode.
The wiring system is designed for maximum reliability and rapid field maintenance. We use industrial-grade M19 connectors for power and signal lines. This modular setup provides vibration and water resistance for power return and robotic arm connection. Type-C panel mounts handle high-speed data transfer for perception system that includes camera, LiDAR, and depth module, while an external XT60 port enables battery charging without opening the tablet.
The rover uses differential drive control for traversal using 4 independent wheels. Each wheel is equipped with a brushed DC motor and an encoder used for velocity PID control. CAN-FT communication system is used inside the rover as it's very high speed, very reliable for electromagnetic interference, and for outside communication with the ground station. A 5 GHz Wi-Fi access point is used, which allows us to transmit high amounts of data over long distances.
Our communication system uses rotors to create a phased wireless bridge between the adjacent computer and the ground station. Every device has static IP address to prevent routing errors and ensure direct data flow. We use identical wide-angle Omni antennas on both sides to keep the connection stable from all angles on rough terrain. The radio cards follow local regulations limiting the transmission power below the allowed 1 watt ARP limit. During the intensive stress test, the system achieved 0 packet loss with a low latency of 1 to 3 milliseconds. This optimized setup provides a reliable foundation of real-time video streaming and rover control.
The control team handles connectivity analysis and efficient driving of the rover. Control management is done by using Foxglove framework. We use custom-built Foxglove panels in order to control properly our rover as we wish. We also make sure the rover responds as fast as possible to user commands, even with latency or interference. An example is our fail-safe system. If the connection drops, the rover automatically stops instead of drifting, of course.
As the science team, our goal is to understand geological context of the ERC 2026 analog region and identify scientifically valuable regions of interest. Using Google Earth Pro and JMARS, we analyze the Hellas Planitia region, investigate its geological features and support landing site selection and traverse planning. By establishing a strong geological foundation before the mission, we ensure that the rover operations are guided by scientific objectives rather than random exploration.
Our sample handling system is designed to meet the official surface, deep and astro-biosampling requirements. The rover collects regolith and rock samples in secured onboard containers, while the dedicated deep sampling kit retrieves and stores subsurface materials separately. For the astrobio task, a leak-proof 100 ml liquid sample container ensures safe transport and contamination control. All collected solid samples are measured using an integrated onboard weighing system to verify sample mass during the mission.
Our science kit features two primary systems, collection kit and the drilling assembly. We designed a sealed rotating helical mechanism. Its outer channels feature an optimized 28 to 30 degree attack angle for efficient scooping, while parametric curves enter the material. A tree-like bayonet cap ensures uniform load distribution and a perfect seal. The three-stage drilling system integrates a 35 mm Forster bit for clean nose, backed by a 30 cm Archimedes screw to prevent jamming during vertical transport. Finally, an 8 mm lead screw precisely controls feed rates based on soil density, ensuring smooth, stall-free motor operation.
As a science team, we previously conducted tabletop astrobiology-related experiments to detect organic molecules such as proteins, reducing sugars and nucleic acids. These tests helped us gain experience in sample preparation, contamination awareness, colorimetric interpretation, and biosignature-related reasoning. For ERC 2026, we are adapting this background to the official astrobio workflow. Our planned procedure includes selecting the most scientifically promising measurement point, integrating pH calibration and measurement, collecting a clean liquid sample, and interpreting the results together with TLC and the provided biological data.
The brain of our science kit PCB is a microcontroller chosen for its modular and replaceable design. We added CAN-bus support for emergency backup communication and a secondary power input from a main rover battery. For drilling and mobility, motor drivers control our dual drive motors, while a separate dedicated driver provides precise control over our gear motor. For soil analysis, the system utilizes a dedicated PR sensor module. Finally, a custom low cell circuit with a 24-bit amplifier accurately measures and verifies sample mass.
Our drone is quadcopter built on carbon fiber frame with 500 mm wheelbase. It's powered by 4 brushless motors with 2-blade propellers, managed by 4-in-1 electro-speed controller. Flight control is handled by open-source flight controller providing dual AMU and Mavlink-based communication. An onboard Jetson utilized for control and communication, as well as enabling autonomous operations. The drone carries wide-angle camera module for live video streaming and photography, while infrared sensors cover all 4 directions for proximity detection. 3 fail-safe layers protect every flight. Loss of Mavlink signals for more than 1.5 seconds triggered automatic landing. A pilot emergency switch activates land mode instantly. Critical battery voltage below 14 volt triggers return to launch. Our rover pilot holds an official EH1 license. Total takeoff weight around 3 kg. Maximum flight time is approximately 6 minutes on 14.8 volt LiPo battery.
Cengaver Rover, building the future one step at a time.